Welcome back to AGR Breaks It Down. I am joined by Gary. I am Dominic, and we're going to get into discussions about the AGR density comparator, of all things. This is an old machine that's been sitting in the lab that I've never personally touched, but you have touched many, many times,
yes.
My understanding.
It's nice to be with you again, and let's talk about the density comparator and what you do with it and how it works.
And from my understanding, it's an incredibly important piece of equipment for the glass manufacturing industry, right?
Well, it is, primarily because glass composition is very important. And in the old days, back in the day, they used to do glass composition by wet chemical analysis, which was time consuming, and it didn't provide the data they needed on a regular basis quick enough.
How long did it typically take?
Oh, maybe 2 or 3 days.
We're talking days. Okay.
Yes.
Yeah.
And glass composition has a very important role to play in the manufacturing of bottles because it does affect various properties of the glass.
Of course. Yeah, it's the foundation.
Yeah.
So why the density comparator then?
Well, it ended up being a quick, convenient, reliable, and very accurate way of monitoring density, which actually is an indirect measurement of glass composition. So it was somewhat of a poor man's system of keeping track of the glass composition on an hourly basis and on a daily basis.
Okay, so you're going from 2 or 3 kind of lagging indicator of what your chemical composition would be to a still fairly accurate.
It's very accurate.
Very
yes.
accurate measurement of the amount of chemical balance you have. But
yes.
now we're doing it on an hourly basis.
Well, it can be done on an hourly basis. I think initially it might have been done frequently, but anymore people are doing it on probably a daily basis.
In fact, I think we have a graph that will show a daily basis of that. But before we get into that, let's talk a little bit more about the importance of that glass composition, what kind of the reasons we're doing this in the first place.
Yeah. It turns out that you have to maintain a consistent glass composition in order for the viscosity of the glass to be consistent, thermal conductivity, coefficient of expansion, even what's called the workability of forming glass containers. That's somewhat of a nebulous term. It's not really something that's measured.
Right.
But if you talk to a man or a person who is forming the glass containers, they know all about workability.
Right.
And they can detect very quickly by just observing the forming machine whether the glass is consistent or not. And they call that workability.
Workability. So, yeah, it's like a catch-all term for
it is.
I
yes.
can form this well,
Mm-hmm.
And I don't have any issues while doing so. It's just
and if something changes, they will let you know.
They'll let you know.
That something has changed.
Workability's bad.
Yes.
Okay.
So it turns out that rather than depending on wet chemical analysis, which takes a long time, as we've talked, density provided them a way of monitoring glass composition more efficiently and on a more periodic basis.
Okay, yeah. So let's go to that graph now. We have basically a line charting out the density per day, and we have an upper control limit, which is just a dashed line well above, and then a lower control limit, which is a dashed line well below. And we have that range, right? We have a range in which we're trying to meet. Now, what would be kind of the limits we're setting here?
This chart that we're showing tracks the glass density. And it's called a control chart. So it has a target value, which is the density that you are trying to achieve on a day-to-day basis.
Your average.
But
that you want.
You know that in the batching operation, you're going to have some inconsistencies.
Some variation.
And so there's an upper control limit, a lower control limit, typically about 20 points above and below your target line. Sometime today, that might be as little as 10 points above and below, depending on how close you want to keep the control of the composition. And you see day-to-day fluctuations due to just fluctuations in the batching operation, fluctuations in making the measurement, But as long as the values of density are within these limits, then you can be reasonably assured that the composition is under control. And if something should happen to the batching operation, it will be reflected in these control charts. And in fact, you can see on this one, about a third of the way along the daily basis, something happened where the density fell outside the bounds. In this case, it was a density far below what you were targeting. That's an early warning indicator that something has occurred in the batching operation. There's been an upset of some sort, and you need to immediately go to investigate that. The ramifications of this would be an upset in your forming operation, this workability concept.
Right.
But more seriously, it could be an indication that you might have cord streaks that are about to show up that could seriously affect the performance of bottles. So this ends up being a pretty good indicator that of watching your composition on a daily basis.
Interesting. So we use this piece of equipment on the daily, and as you were saying in this chart, between days like 35 and 40, we dip below the lower control limits. That, I'm sure, sends off alarm bells at the plant. What would be kind of like the first steps to bring this back under control?
Well, the first thing would be to go into the batching operation and to begin examining the batch mixing, the scales that weigh out the various components of the batch. You might even want to analyze the batch components to make sure there hasn't been any contamination of one raw material being inadvertently dumped into a storage bin of some other raw material.
Mislabeled,
And by doing that, and in doing it immediately, you can help to offset problems.
Okay. So there's a little bit of a checklist there.
Oh, yeah.
But we want to talk about the density comparator, right?
That's correct.
So let's talk about that. In fact, we have an image of a density comparator here. It's a fairly simple device altogether.
It is a simple device. It consists of about a 5-gallon tank of water into which are inserted test tubes, a little bigger than normal test tubes, that contain a mixture of oils. And these oils are mixed so that the density of the fluid is around 2.5, which is the approximate density of most soda lime silica glasses that are manufactured today. There's a heating element in the water, and by slowly heating up the temperature of the water, that temperature will progress through the wall of these test tubes and heat up the oil at a very controlled level. And the idea is to put your unknown glass pieces together with some pieces of glass whose density is very accurately known. You place them into the oil, and you adjust the composition of the oil at room temperature so that these pieces float. Then by slowly increasing the temperature of the oil, the density decreases, and eventually these pieces will begin to fall through the liquid, the oil, and as they pass across a reference line, which is indicated on this picture as a red line on the test tube, you measure the temperature at which the unknowns pass the reference line compared to the temperature at which the standards pass the reference line. You can then use this simple equation, which is found in an ASTM standard, and as long as you know the coefficient of density increase, that's C sub P, you can then calculate the density of your unknowns. It's a very simple method. It's very accurate as long as you have accurately known standards.
So we're changing temperature, and based on the changes in temperature, we're able to figure out, because we already know the density of our standard. We're able to figure out the density of the unknown sample, or the glass that we're currently producing. And that's all it is.
Yes, and then you simply plot that number on a daily basis on the control chart we already showed. And as long as the density falls within known acceptable bounds, you're good to go.
Okay. So now that we kind of know the basics of all this, what we really want to talk about is some of those operational considerations.
Yes,
right?
Because they're very important.
They are important, yeah, incredibly important. In fact, the first one I think is probably one of the more frequently asked questions we get all the time, which is glass color, right? They want to have the exact same color for their standard as their glass that they're producing because they think it's going to affect the densities.
Yes.
Now, is that true or not?
No. Well, glass color can affect the density. However, when we prepare these standards for use in the density comparator, we take the color into consideration.
Mm-hmm.
And so the value of the density that we supply is independent of the color. And in fact, when you think about the pieces of glass that are in these test tubes,
mm-hmm.
you would actually like to have the color of the density be totally distinct from the color of the unknown glass so that you can clearly distinguish between the two.
Oh, because they're both falling past that reference line. It's not like you can mark them, right, with like a marker.
You can. However, that introduces some irregularities in the glass surface that could become problematic. Usually they're not. So yes, you could mark letters or numbers on these pieces of glass to differentiate standards versus the unknowns. But it's so much easier just to use it by color.
So if I have an amber piece of glass as my standard and flint or green is my unknown, it's easy to say, okay, the amber piece, my standard's falling past that reference line. I know exactly where that goes into the equation. And then once my unknown piece crosses the reference line, being a different color, I know exactly when that is.
Exactly.
To kind of having to pay very close attention as I pull them out, identify which one's the sample, which one's the standard.
Even if you were to etch or scribe
mm-hmm.
an identifying mark on the standard, once it's in the oil, sometimes those marks are hard to see.
Mm-hmm.
And it's so much easier just to use a standard of a different color than the unknown glass that you're trying to measure.
Okay. And it has kind of a negligible effect on...
There's no effect on this.
No effect?
No,
okay.
None whatsoever.
Even better.
Yeah.
Yeah. So in that case, might as well do it, right?
That's
two different colors. Cool. So now we have that out of the way. Let's talk a little bit about the settling temperature. Now,
yes.
The settling temperature is a specific point, right, where that the temperature is going to be when you cross that reference line, or is it something?
Yes, that's what's called the settling temperature.
Mm-hmm.
The operation of the comparator is accurate between about 18 degrees centigrade and into the 30 degrees centigrade range. It's a fairly wide range of temperatures where the coefficient of density change remains constant.
Mm-hmm.
And so you can operate the density comparator anywhere of convenience throughout that range. One of the things I'd like to emphasize is that some people like to operate in the lower region of the range, which if you're using city water
mm-hmm.
as your coolant, by the way, we need to talk about that. I forgot to mention there's a heating element in the water bath.
Mm-hmm.
There's also a tube in the water bath through which you can run tap water in order to cool that bath down after you do a run so you get prepared to do the next test.
Okay.
And so you need some means of cooling that water bath down to the appropriate starting temperature.
It would take too long to just let it do it.
In the summertime, if you're using city water, you may not be able to get it down low enough to meet where you're wanting to start the test at. And so some people will put ice cubes into the water bath.
No kidding.
And that's just, you may think that it works, but my main concern is you want to assure an equilibrium or uniformity between the water bath and the temperature of these oils in the tubes. And by artificially cooling the water bath, you may not have the uniformity that you need
mm-hmm.
to do an accurate test. And so it's so much easier simply to adjust the mixture of these oils to raise this settling temperature. Typically, we recommend somewhere between 25 and 30 degrees centigrade.
Okay.
That way, you have enough latitude in the use of the density comparator so that you can start at a low enough temperature where the pieces of glass are floating,
mm-hmm.
and then you can heat up slowly enough to ensure the consistency of the water bath and the oil temperatures.
So as long as we're within that set range, which I'm sure you could find in the operator's manual.
It is.
It's just whatever's convenient to you.
Yes, and you should adjust it to be convenient for you, depending on the time of the year and whether you're using city water to cool the bath or using well water.
Mm-hmm.
Absolutely, you should never use artificial means of cooling that water bath.
Okay, so
such
don't
as
throw
ice
cubes in.
Please don't do that.
Just use the cooling tool.
Yes.
Okay. So all good points on the settling temperature. Now, in kind of relation to that, we have the heating rate. Now, you have that heating element inside, and there's a pretty rigid standard for
Yes.
what we allow for the heating rate. If you were to say, heat this guy up at a centigrade a minute, is that too hot? Is that too
Okay.
cool? What's the deal here?
According to the ASTM standard that covers this method, you are supposed to cool the temperature of the water bath and the oils to a value about 2 degrees centigrade below the temperature at which you expect the settling value to be.
For the standard or for?
Well, for either one.
For either one, okay.
Where the first falls, whether it's the standard or the unknown.
Mm-hmm.
And so you cool down about 2 degrees centigrade below, and then you can initially begin the heating rate on a manual setting on a density comparator, which is a fairly rapid rate of about 1 degree centigrade per minute.
Mm-hmm.
But once you reach about 1 degree centigrade below the settling temperature, you should turn off the manual, turn on the automatic, and that controls the heating rate very accurately to 1/10 of a degree centigrade per minute.
Okay.
And that heating rate has been found through experimentation to assure that you're getting good uniformity between the water bath and the oil temperature.
Again, so you're trying to get that equilibrium.
Yes.
And with that accuracy of the results, right? So if the oils are at a slightly different temperature than what the water bath is,
it can cause some problems. And the main issue is you should assure that the oil is uniform in temperature across the diameter of the tube. And so if you're heating too fast, you may have a higher temperature along the inner walls of the tube and a cooler temperature in the interior of the oil. And you don't really want that because you want the oil to be as uniform as possible. Therefore, the heating rate of 1/10 degree centigrade per minute is specified in the ASTM standard.
And that's why it's set to that automatic value from the knob. Okay, so manual, bring it down to fairly close to what is expected, about a centigrade set away, and then turn on automatic.
Yep.
Because you don't want to be waiting. If it's a centigrade, 1/10 of a centigrade per minute, and you're trying to wait for a whole centigrade, that's 10 minutes that you're sitting there.
Yes.
And you have to actively watch the glass pieces fall across.
That's correct.
Okay. So that's important, obviously. We don't want to be sitting there too long, but we also don't want to upset the balance of the test and the equilibrium in the tank.
So let's go to that actually in our next concept, and that would be the difference in temperature between the standard and the unknown.
I believe we called that the temperature spread. We can jump around. That's
all right. That's fine.
Yeah, let's do it.
Because it's germane to this discussion right now.
Certainly.
You would like to have the standard and the unknown fall no more than 2 degrees centigrade difference in temperature. And it actually depends, or it is important to what you've just mentioned. At 2 degrees centigrade difference, with 1/10 of a degree centigrade per minute change, that's 20 minutes.
20 whole minutes.
And sometimes people may get impatient, and they'll go from the automatic back to manual just to speed it up. And that could disrupt the equilibrium and temperature of the oil.
I mean, that's a whole episode on TV, about 20 minutes.
Yes.
Yeah, so you're sitting there watching glass fall. That's not very entertaining.
Yeah, it's like watching paint dry or grass grow.
Yeah.
So it doesn't affect the accuracy of the test. You could have a temperature difference of 4, 5, 6 degrees centigrade.
But no one's waiting an hour.
No. It's not reasonable. It's not efficient. So you'd like to have the standard and the unknown fall as close together as possible, which relates back to glass color. If they're falling very close to one another, you want to be able to distinguish the two. So you want to keep this falling or this settling temperature, that difference, within 2 degrees centigrade. Now, you accomplish that by specifying what your expected density of your production glass is, and then we can make the standards to match that, or at least very closely match that. And if you change the composition through differences in raw materials, or you purposely change the composition, you need to know what that new density is so that you can then determine if your existing standard will work efficiently,
Right.
or whether you have to change it and get a new standard. Exactly.
Interesting. Okay. So let's jump back then.
Sorry we got off target there a little bit.
That's great. I'm happy to have that discussion. So we talked about the heating rate, talked about the temperature spread. Let's move to a new topic here about the sample tubes.
Yes. It's very important, critical, that the standard be in the same tube as the unknown. And the reason for that is you can adjust the composition of these oils by adding one or more or less of the what is called heavy and light fluids.
Mm-hmm.
If you have the standard in one tube and the unknown in a second tube, those settling temperatures can be affected by slight changes in that composition. And so you're going to be comparing apples and oranges.
Different environments. Okay, so they're independent at that point. They're not.
That's correct. They're not tied together.
Not tied together. So whenever you measure, despite there being like 5 or 6 different vials,
right,
test tubes inside the density comparator, when measuring that unknown and the standard, same tube.
Right. Now, when we supply standards, sets of standards, we supply 5 pieces of glass whose density is very, very close to each other. So you could put one standard in each of those 5 tubes, one standard piece, and run all of the glass from, say, various furnaces you may have. And so you can optimize the utility of this device by separating out these standards. However, when you're measuring that temperature difference between the standard and the unknown, it has to be within that same tube.
Okay, so parallel tests.
Yeah.
Standard, sample, one tube, another standard, different sample, another tube, and so forth.
Right.
So
now,
we can test all these different, like you said, runs or furnaces, whatever the case may be. And that reduces that whole wait time of 20 minutes or so down to what could have been, if you're doing 5 different tests, an hour and a half or something like that, down to just 20.
Just something very reasonable. Yes.
Of course, now you have to pay attention to 5 different
yes, exactly. And you have to be able to measure or detect the temperature at which these pieces fall past the reference line. In the old density comparators, it was a digital or analog thermometer. Well, today you have digital thermometers that are very accurate, and it makes things a whole lot easier.
The beauty of the modern era.
Yes.
So, okay. Alongside the sample tubes, we have sample preparation. Now, this can mean a couple different things, right? This could be contaminants on the surface. This could be things you don't want inside the glass, such as seeds, right?
That's correct.
So all boundaries of that. So
there is a prescribed procedure in ASTM where you clean these samples meticulously and dry them meticulously and let them come to room temperature before you put them into these tubes of oil. Any contaminants such as fingerprints or mold dope or just ordinary greases from lying around in the laboratory can contaminate these oils. And the problem here is not so much that it will upset the coefficient of density change as much as it darkens the oil. A big issue is water. When you clean these items, and if you use something that's fairly warm, when you set the pieces out to dry and it's a humid environment, oil, very, very thin layer of water can condense on the samples. You may not even detect them. When that goes into the oils, it's not miscible, and it can turn these oils dark. These oils are also bromine compounds, and they are sensitive to ultraviolet light, and that will darken the oil. Again, it doesn't affect the accuracy of the measurement, but it makes it very, very difficult to see the pieces of glass as they fall past the reference line.
You're actually mentioning the age of the oil is another thing that can affect this, right? So this was actually one of our talking points. UV light, water, age, all of that can affect the kind of opacity, I guess, of the oil or how dark it is, which, as you just said, doesn't affect the test results.
Right.
But now I can't see my glass.
You can't see it as clearly.
As clearly, sure. Especially if I have like an amber piece. I'm sure that's real difficult to see.
Now, back to the original question, and that would be
prepping those samples.
You want to select pieces of glass from bottles that have a fairly consistent degree of annealing. Usually these are selected from the heaviest pull shop of the furnace,
Okay.
and from a glass container from the middle part of the aleer, so that the annealing is consistent from day to day. That way you don't have to re-anneal these pieces. But the big consideration is you want to make sure your sample pieces of unknown do not contain seeds or stones. Now, density is simply a measurement of the mass divided by the volume.
Right.
The mass is easy, but the volume,
That's the hard part.
if you have a seed inside this piece of glass, the volume isn't going to change, but the mass will. Same thing with stone. If it's interior to these pieces of glass, you won't change the volume of those little pieces, but it will change the mass, and that'll upset the measurement of density. So you won't get a measurement of your composition, you'll get a measurement of some artifact. Now, some people will also be very careful to avoid chord streaks to make sure they're actually analyzing the composition of the glass. Other times, you may want to include pieces of glass from a container at random, so that if there is some undetected chord streaks in the bottle, if, say, you select 5 pieces that you're running in the tube, the spread of temperature at which these pass the reference line will increase because of the changes in composition of one piece that might be chord-free compared to another piece that might have a little bit of chord compared to a third piece that could have a lot of chord in it. So instead of your multiple pieces falling past the reference line together, they'll spread out in temperature. And that's a pretty good indication that you might have a problem.
Might have a problem with chord.
Yes.
And then you can go back and, okay, so I see how you mentioned earlier how this has relation to chord. This is what you were talking about.
Yes.
Is this right here.
Yeah.
Not necessarily that we're testing one sample and we can measure the differences in chord. We have to measure several samples,
That's
randomly
right.
selected. And if they are falling at different rates, assuming it's the same furnace draw and all that,
Right.
that we have a chord issue.
Yeah, there's something wrong. Now, most people will only select one piece of glass from the container and make sure it's from a chord-free, seed-free, stone-free area. And then they get a pretty good idea of what's going on with their composition and consistency from day to day. But other times you can utilize this in a different way to be kind of an early warning system of chord. Now, of course, today, a lot of people routinely cut ring sections, and so they're looking for chord in polarizing microscopes. And so you don't need this early warning device as you did maybe decades ago.
I see. Yeah, and it's still better to measure via the polarizing lenses because you can actually get a value of how much stress is caused by the chord, and whether it's problematic.
Yep.
But you can still use this detection method alongside, if you have the extra sample tubes to cover pieces. But, well, that's interesting to know about. So I think that covers most all of our considerations. I don't know if there's too much else. I know this, like we said at the beginning, this is a fairly simple piece of equipment. What it's there for is to detect the density, and that changes on potentially a daily basis, which is why we have those control charts, as you called them, right? And that's pretty much it. We're just looking to find a efficient method of monitoring our chemical composition over time via density.
Yes. And it goes back to that very simple equation. The coefficient of density change is a very well-known number for a mixture of these oils that cover a range of densities that are broad enough to cover borosilicate up to some of the more heavy soda lime compositions. That's a very well-known number. It's in the ASTM standard. Then all you want to do is measure that temperature difference, and you multiply that by this coefficient, either add it or subtract it to the density of the unknown or the standard, depending on whether the pieces fall first or second, and you calculate the standard of the density of your unknown glass, your production glass. Very, very simple. And as long as you take into consideration these factors that we talked about, you can depend on these values and you can make sure that your composition is what you want it to be.
Cool. Well, thank you, Gary, for being here. That's it for this episode of AGR Breaks It Down. Hopefully we'll be able to get back into the studio a little bit earlier next time because we're getting close to the end of the day here. So I'm ready to sign out. How about you?
We're done.
We're done. We're
Okay.
done. Catch y'all later. Thanks for tuning in.